We are happy to have Xingyang, who will tell us about the stringy approach to symmetric topological field theories.
Thanks for inviting me. It's very good to come back. So yeah.
Can get more light on the blackboard.
Oh yeah. Thank you. Yeah, since it's a blackboard talk, so I might do a very bad job on citing papers, give you references. But the whole talk is basically based on these papers by me and some very nice collaborators. And also you can find some other interesting papers by some other groups which doing similar works. I will maybe mention one of those if I feel necessary. So basically this talk is it's more like a overview talk about the recent work, I would say in the past 2 years, like about the string theory or top-down approach to generalized global symmetries. And this whole work basically can split it into, I would say, 2 aspects or perspectives. One is how you can capture, theoretically speaking, you can capture a global symmetry. Usually it's finite symmetry into a one-dimensional. If you have a D-dimensional QFT, you can try to capture this symmetry into a one-dimensional higher topological field theory because the topological nature of the global symmetry, thanks to the celebrated work by Galto, Cyberg et al. And another perspective is that actually you can always use these topological operators to try to capture or to generate this kind of global symmetries. And so these 2 aspects actually both enjoy a string theory approach. Like how can we derive SymTFTs for these generalized symmetries, or how can we just derive the topological operators from the string theory objects? And this is how I will arrange my talk here so that I won't forget where I am. So in the first part, I will try to review some field theoretic facts of SymTFT works and how the topological operators in the symmetry QFT tell us about the global symmetry structure in the QFT, which is associated to this symmetry QFT. And then I will talk about some very general idea of how the QFTs can be embedded or engineered from string theory. Then based on this engineering of QFTs, I will talk about how the SymTFTs and topological operators for the generalized global symmetries of these QFTs can be engineered from string theory. And then I will give you some examples. If time permitted, I will give you example in diverse dimensions, but if not, I will just take my favorite example to say this. Okay, so let's start with the first part. As I said, due to the celebrated work by Galto, Cyberg et al., we built a very nice picture actually about topological operators to the global symmetry of the theory. So in most cases, if your QFT enjoy a global symmetry, then you should be able to build a topological operator which generates this global symmetry. But there are some subtle cases like subsystem symmetry, which is not topological, but I won't touch that part in this talk. And then since given this topological nature of the global symmetry, it's very natural to guess or to say that, oh, is there any topological field theory which can capture this topological nature of the global symmetry? The answer is yes. Usually this is people talking about the notion of the SymTFT, okay? Instead of to be quite abstract, I will try to give you an example. Let's consider 4D and 4 Lie algebra SU2 superMUs. And this theory, so at this level, you only know the Lie algebra, which means you only have the local information of this theory. By saying local information, I mean the spectrum of the local operators and the correlation functions among them. And then after you picking the global form of this Lie algebra, let's say you can pick SU2, or S3, SO3, plus or minus. These 2 are different because of the discrete angle, which is defined by or due to some work by Tachikawa and Cyberg et al. And then you can say that, oh, actually, even if I give you the local information of the symmetry, sorry, the local information of the theory, I still need to give you some more information about the global structure of the theory. so that I can fully specify what theory I'm talking about. And the difference of this theory, the global structure of these different theories, are basically the information of the one form symmetry, the higher form symmetry they are talking about. So the SymTFT you write down to capture the one form symmetry information of these theories is a one-dimensional higher 5D theory. With two one-form fields, B2 and C2, and at this level, they are just the U1 fields. But if you write down the equation of motion of these fields, you will realize that they're actually they are actually constrained to be a Zn finite value of the gauge field.
Is equal to 2?
Yes, right. Yeah, thank you. Yeah. Here in this case is n equal to 2, but I would just writing n here to be generic, but I will just focus on the SU2 cases. Thanks. And then we can talk about this SymTFT, which saying that I can actually give you the topological operator spectrum in the SymTFT. There are basically two operator, or I would say the two operators which can generate the spectrum of the this thing is IM B2 exponential IM C2, where M and N are from 0 to n minus 1. Okay, because the equation of motion tells you that if this is a multiply of capital N, or in this case it's just 2, it will trivialize this operator. And then, because this is, and then I can try to do something very similar to the quantum mechanics, because TFT is basically some version of the quantum mechanics, right? You will realize that actually, if I write down the canonical conjugate momentum of this B2, it's the C2 field, maybe up to some factor here. And then you can say, then you know that B2 C2 has a non-trivial commutator here. So that you know there are actually, if I write down this operator as UM, this operator as Vn, then you have this commutator, Vn UM, it's up to some exponential 2 pi mn over capital N. This is defined on sigma, this defined on gamma. This will give you the linking or the intersection of these two surfaces. So these two operators are actually generating a non-trivial commutator, because B2, C2 are canonical dual to each other in the same under the same TFT composition. And then I would say that, okay, then how do I know about the global symmetry in this 4D theory by from given this SymTFT? The thing you do is to build a picture like this. This S5 is in the this S5 is defined in a 5D block, and then you put your G equal to SU2 V algebra superimmunes theory here. Here we define some topological boundary conditions, and the different behavior of these topological operators under these boundary conditions will tell you the one-form global symmetry information of different theories with the well-defined global form.
So yeah, talking about 4D and equal 4.
Yeah.
But really, you're not using that, right? So here you only care about gauge group essentially, right?
Yes, right. If you, you can just talk about pure gauge theory in 4D without any other things. As long as you have non-trivial center of the gauge group to discuss the one forms. Yes, exactly.
And so this TFT is supposed to capture just one form symmetry. So
yes, in
zero form symmetry is a
in this case it's just if you only write down this term, you will only care about the one form symmetry of the theory. If you want to discuss other symmetries, you need to put extra terms here.
There's actually difficulty in writing a SymTFT for continuous zero form symmetry.
Yeah, right.
Only people recently have done that.
Yeah, right. Recently, yeah. But I think there are some subtleties in their work. Yeah, right.
And so, for instance, if I want to capture also supersymmetry,
If it's R symmetry, then I
oh,
would
there's
say
R symmetry here, but
Yeah,
if we're talking about that,
Yeah,
there's the supersymmetry, right?
Yeah.
Yeah.
So,
space-time symmetry is even harder. Like supersymmetry is like one kind
Yeah.
of
So
space-time
there's a hope that if you want to do like supersymmetry or space symmetry in general, then the SymTFT would be like gravity theory or supergravity theory. But it so far just works.
Yeah. So the general idea is that once you have a global symmetry in a D-dimensional QFT, you promote it to be a gauge symmetry in one-dimensional hyperbolic, and you introduce the gauge field associated to that gauge symmetry, or something like that. Like this B to C2, they are dynamical field in the 5D, and they can be think of as the background field for the one-form gauge symmetry in 5D. So if you have supersymmetry or some other space-time symmetry, as you can say, you try to promote those as gauge space-time symmetry, which will force you to talk about gravity theory in one-dimensional height. Any other questions?
These sigma and gamma, they're right now, they're unrestricted. I can take any path I want.
Oh, these are just the 2D surface where you define this. So where this operator are supported.
But maybe Jack is asking like when you write when you write a commentary, they are restricted given time slice.
Yes, right.
And this
so
intersection number.
yeah, in this okay. So maybe this is better. This is easier to understand. Like if you are doing if you define this as the time direction, then you do the radial the quantization of the SymTFT along different time slices, and then this is the equal time commutator along.
There is an
different
I
time
missing.
slices. Yes, right. Yeah, thanks. Yeah. So in this picture, the local information of the 4D gauge theory is defined on this. Usually, it's called physical boundary. And to fix the global structure of the theory, we define the topological boundary, or call it gapped boundary if you are more class better inspired. And then let's take example. If I take directly bound condition for B2, because I know B2, C2 are canonical dual, I mean it cannot be simultaneously fixed on some value. So C2 should be free or Neumann bound condition on this gapped boundary. And then you can see that this operator, depending on B2, when it touched the gapped boundary, or when it touched the topological boundary, it will be trivialized. It's not dynamical anymore. It cannot, if you have a B2 operator, something like this, it will stop here. It won't keep fluctuating, or it cannot continue its word volume to the word volume surface along this thing because its profile is fixed.
So what are the boundary conditions at the two ends for B and C fields?
Sorry, you mean what?
You have B and C fields in
Yeah,
the bulk.
right.
So what
Yeah.
are the boundary conditions at the two ends?
Oh, so here you always pick the enriched Neumann boundary condition, but on the topological boundary condition, you pick one. You pick directly boundary condition for one of the field, and the other one, because of the canonical dual quantization, it has to pick the free one.
And below, you said
Below is always the enriched Neumann boundary. It's just the Neumann boundary condition. You can think of as that.
And so what are these boundary conditions? Is it enriched Neumann?
It's just the Neumann boundary condition. You can just think of they're always free along this physical boundary condition, and coupled to the theory defined on this physical.
Okay, so but what is the complete system? Can you write it down? So the 5-dimensional action, the 4-dimensional action.
Yeah.
Yes.
I think Massimo wants you to write, for example, the boundary condition setting B equal to what?
Yeah. B
Oh,
equal to
okay.
what?
Yes. Okay. Yes. So in that sense, you can write something like this: B2. I would say B2 star, something like that, along the boundary. So you fix the B2 profile into you fix the B2 to some fixed background field profile along the gapped boundary. and the C2 are just free.
Yes.
And then after you shrinking the SymTFT.
But I don't understand what happens at the super-Yang-Mills boundary, because so far I have a decoupled theory, right?
Yes.
I mean, can you write an action that has everything in there, like a Schwinger would have done, where you write an action, vary, impose that the variation is 0, get boundary condition?
I think yes, but I don't have that in my fingertip.
I think, yeah. I mean, you just that the B2 on the bottom boundary just sums over.
It B2 on the but
Couples to the super Yang-Mills,
It's-
and they're
so
integrated.
how is it coupled? Because it's,
I don't know how to write a concrete form exactly. It's like the background field for the Lawson line operator. So you can just try to couple it. It's like if you have a point charged particle, then you can couple it to the background one form field, right? It's like the similar thing here. You can have some Lawson line
yeah,
operator here.
I mean, and if you have a two form, you can couple it to
Couple it to a line.
to a line.
Like,
But how does it? It seems that it's completely decoupled from the SU2 theory, though. There is nothing that relates one to the other. I don't understand why. I mean, I could have put on this boundary anything I wanted, right? So far. So what's the connection with SU2 super-Yang-Mills?
Don't you want to say the B2 couples to the one form symmetry in the SU2 super Yang-Mills?
yes, after you. But I think that only happens when you shrinking the after you pick the gap definition, then you know how it couples.
No, but that's from the delta function. But the delta function selects the particular background for the
Yes,
one-form
right.
symmetry. But
And
at
then-
the bottom, I think Massimo is just asking at the bottom on the physical boundary, how does B2 couple to the super Yang-Mills?
Yeah, that I'm not sure. I'm not sure about the concrete form of how it coupling actually. But ideal would be it's something like it coupled to the one form symmetry charged object in the Ford, which is the Lawson line. In
Yeah, but I
sense.
still don't know.
Yeah, it's like if you have some. Let's see if I can write it down.
Just B2 wedge F.
I would say something like this. B2 wedge star F.
You have where do you put the trace?
Because B2 is a billion, right?
Yes, I mean
It's a billion, right? It's a
F is
big
F
difference.
is
It's
SU2.
Yeah, right.
Yeah.
Let me see. Yeah. Oh, it might be something like this. If you have a, let's say if you have a non-abelian field A, and then you can try to, split it as a, yes, something like this. This is for series towards if you want to talk about SU and mod ZK, I would say. So you can try to split this non-abelian field to be sorry, this SUN. Sorry, this is some UN fraction, and then you can split it into SUN and the U1 part. And then you want to realize this SUN mod ZK gauge group, which you know there is some form of ZN mod K1 form symmetry, something like that. So in our case, it will be SU2 mod Z1 or mod Z2. If it's mod Z2, it will be SO3 plus or SO3 minus. But this is a trick. You can write down this global form of the theory under the UN gauge connection and split it into the SUN part and this part. And this will be the gauge connection, which give you the local information of your SU and supermuse theory. And the way to connect this B2 or C2 to this field is basically something like you write down some particular A field and couple to B, or it's a dual field coupled to C.
So if A is not there, right? It's
A is, so it's not in the superimage action, right? And then it's not the model cases.
in the SQL theory, we only have A tilde, right?
So I think what Xingyang wants to say is that you are summing over all possible boundary values of B2 at the bottom boundary. And depending on the boundary value of B2, you are dealing with different gauge bundles for the superamines, either for structure will be equal to SU2 or SO3.
But how?
So that's how they couple, like different values of B on the lower boundary tells you what is the actual gauge group that you should be using to define the pattern to go, like SU2 versus SO3.
But there is no way of writing a coupling that will tell me that.
Yeah, because it's because it's a discrete. This is a discrete object.
So it's, how would I know that there is even an S superimage? I mean, I have the
Yeah.
S5 theory with some B at the boundary, so I could have said, no, there is no superimage, there is just B.
You could.
And,
Yeah, then you are talking about some SSP, like some trivially capital or some just.
But the superamines part is what they meant by enriched is this pattern function of the superamines.
It's like you can start with the Purge function without turning on the background field.
Yeah.
And then you can promote it by saying that I want to couple a non-trivial one form symmetry background. And this, and introducing this thing is something I'm called enriched unconditional.
but how do you introduce it? So what is 0B? I mean, I know how to write that integral, right? But how do I put B into that path integral? You know, I believe that the great revolution of the 17th century was that the question change was from how to how much. So here I'm not continuing, I don't understand anything. It's like,
So I think
it's like philosophy.
So I think the way is like you first write a local like the superamines term, but with this A field, like you try to write a UN gauge connection about this thing, and then you tell me how the U1 part of this UN is coupled to B2. And after you do the passing,
talk about it that way. So Massimo, maybe say it differently. So the idea is that it's true that you don't have to put the superamines. You can talk about S5 where you have division boundary condition for B at one end, also at the end, and then you can couple the superamines by multiplying depending on what value of B you pose on the lower boundary, multiply by the boundary function of the superamines either with SU2 gauge group or SO3 gauge group, and you sum over the possibility for the boundary value of B on the lower slice. And that's what defines the full theory on this S5 with boundary, the enriched boundary.
So, I mean, this that depends on the topology of the four-dimensional manifold. Right?
Yes,
right.
right.
So depending on the topology, sometimes the boundary function for SU2 versus SO3 is just the same. For example, that happens on
if you
S4
don't have
R4.
if the homology of this S4 is not, it's not.
That's right. So they make difference on CP2, S2 times S2.
So they're saying you take Z
Yeah.
with some in like gauge bundle.
Yeah, that's right.
One of the choices that
Yeah,
you're given
yeah,
M4.
yeah.
Then you can multiply it by the Z
Yeah.
of S5,
Yes.
by the polynomial S5, with a given boundary condition
That's
for
right.
B, and then you can also form this sum of
Exactly.
Z1, so Z of super M is then Z of B,
Yes, yes.
summed over all
Exactly,
possible
exactly.
values.
So we're said differently. In which boundary condition is a linear combinations of the derivation boundary condition where the coefficient are given by the partition function of the superambulous with different gauge bundles.
Yeah, or you can think of like abstractly if you have four manifolds that make this homology class, which you can define non-trivial magnetic or electric flux. Like the magnetic flux will tell you the different boundary conditions, like whether you
I
have
would prefer to think about it concretely more than abstract.
Could you write formulas that Massimo said? So Z is equal to Z super n minus.
It's a boundary condition, right? So we're talking about boundary condition for S5. The boundary condition for S5, there's a basis given by just derivation boundary condition for B, depending on the value of B taking, it could be 0 or 1. The enriched boundary condition defined by the superambulous is a linear combination of the derivation boundary condition for B, where the coefficients are the partition function of the superambulous on the gauge bundle, and the choice of the structural group for the gauge bundle is determined by the value of B. So either SU2 or SO3 in this case. It's just two terms. The coefficient are given by the two different functions.
Why this was useful? What did they gain from this?
Not for this case. I think in this case it's useful in the sense that this discrete theta angle can be described in this language directly from the TFT.
Say what you gain compared to say the Toft box, Toft boundary conditions, or even according to whether you have S2 or S3, different twisted boundary.
Right.
We get more than that.
I mean, this is just kind of more systematic way to understand the features of the symmetries, like what Xingyang is going to talk about, for example, the theta angle. And
That depends on M4, right? So shouldn't you look for the M4 with the biggest H2?
Oh, I mean,
If you want to get more information about it.
Yeah.
So shouldn't you look at indeed what is T4?
Yeah, but alternatively, you can also just talk about S5. So it's true that you can detect all the information that that's captured by the SymTFT, but just restricting in 4 dimension and consider most general manifold. That's true. But alternatively, you can also capture the same information by action in the 1 higher dimension.
I mean, by this information, what do you mean? Because of course you don't know what is the partition function of the superambulous theory.
Yes.
And even after all of this, you will not know.
Yes, you still don't know. It's just it's something like the different choice. It's just the coefficient of.
But you will know how it will respond when you put the theory on a different manifold. Then the partition function, you know how the partition function respond to the fact that you put on different manifold. For example, pick up different phases when you do a background gauge transformation on the one-form symmetry background.
So I mean, you pick up the information about say the anomaly.
For example, this N is capturing the mixed anomaly between the
anomaly between the so
I think part of the motivation for this is originally from condensed matter theorists, where they are not comfortable with talking about theory with anomaly in its own space-time dimension. So they want to say, whenever you have a system that has some anomaly for some global symmetry, this is the system that actually is the boundary of a higher dimensional system. So this is like a realization of that picture in the continuum.
Yeah, but in that sense, they usually talk about an invertible TFT much higher.
Yeah.
And then if you generalize this to non-invertible TFT in higher dimension, you talking about some SymTFT and polarization. So Yeah, so in the sense of the TFT quantization, you can try to say, you can say something like this. This B physics is something can be written as a relative theory, which is corresponding to the state in the Hilbert space under the quantization of the TFT. And then pick different boundary conditions is just to choose the state to make a inner product of this thing. This topological boundary condition will tell you the background field profile of B or C
So
field.
yeah, he's writing down the formula right now.
Then you know. Yeah, right. You can, yeah, right. So the relative theory is basically something like the linear combination of these three global forms up to SPT stacking. But but basically this is what you can just said in terms of the Hilbert space language. I know it's still quite abstract, but
Is that B star or something?
sorry, where? Oh yes, right, yeah, B star, yes, right. Yeah, sorry, yes. This should be a certain value of the B2.
Yeah, Jack is saying that in argument,
Yes,
B2 is
here should be a B star, which you already know the background field profile. And what happens to the C2 operator in this language? You know that C2 is picked a free boundary condition, so it still keep being topological everywhere, even on the boundary. So the C2 is still blinking here, even if you put C2 on the C2 can still be defined, well defined without reducing its dimensionality on the cap boundary. And if you shrinking this SymTFT step, let's try to write down the shrinking. Let's try to write down this shrinking line in terms of a surface. Now B2 is become some operator here. Then C2 is linking with it. So this is the Euro picture how a charge operator is mirror the charge of the object which is charged under the symmetry. So in this case, C2, this V operator, the Vn is the symmetry operator, and Um is the charged object. So this is Wilson line. In this case, when you talk, this is the Wilson line operator come from the B2 operator or come from the operator. So in this case, you know you are talking about a SU2 global form with electric Z2 one-form symmetry. Let me write it this way: one-form symmetry electric. And then you can do other boundary conditions. You can pick C2 to be derivative, then you fix the background profile coupled to the top line. In that case, you have the SO3. In that case, you have the SO3 plus. We are talking about the magnetic one-form symmetry. And the differentiation in terms of this way is that you pick another topological boundary condition to make the inner product with the relative quantum field theory state in Hilbert space of the TMT.
So the idea you study some theory on a four-dimensional manifold.
Yes.
But you don't know some global properties. After that, you lift it to 5 dimensions, introduce some topological brane, and this topological brane selects your global properties of your theory.
Yeah, I would say this is more like a trick you can do, but this 5th dimension is not necessary. You can make everything precise in 4D. I don't remember the formula, but I think it's something along the lines I was writing. Like you can write, you can first write a UN bundle and then try to split it into SUN and the U1, and then how you constrain that U1 to be maybe you gauge some DK or DN part of that U1 will tell you how the 4D action look like. Like yeah. Let me try to remind myself. I think I should be able to write that thing. It's I think the detail is in the original paper by Cyberg and Galdo et al. This generalized global symmetry thing. I think it's basically if you have a UN, this is SUN, this is a U1. You try to write a theory with SUN on ZK. So what you would like to do is that try to make sense of the gauging ZK performance purely in 4D. So you write something like this, and then you try to couple the thing, and then you write something like, I think this is a term you need, something, and then you might also need some term like KB2 minus or plus DA, and then you introduce a Lagrange multiplier of this thing. It might be some other term, but and then you have the superimmunes term for this A field.
Not equal.
And then in the end, this extra term will tell you how the UN bundle is constrained to be some certain SUN multiplicity. Up to some gauge transformation should be defined. Yeah, sorry, I don't.
After integrating.
After, yes, right, exactly, yes, after integrating out this thing, yes. And then you will know how the B2 is dynamically coupled to the.
But what it does
not
is
really
just
dynamic
select the
couple,
gauge.
yes,
What
yeah,
it does
right.
just select the gauge.
Yes, right. What it does is just after you're writing this thing, you select a gauge bundle inside SUN. After you integrate out the U1.
Either SUN or SUN of ZK.
Yes, right, yeah. So I'm not sure whether this is some term Maxwell is looking for, but I think it should be along these lines.
And F is just a Lagrange multiplier, you are just writing the first order. Okay, that simply sets B equal.
Yes, right. It's simply like B is some ZK value thing, or yeah. And also you need to introduce some one-form gauge symmetry transformation to make the whole action well defined. And then this is actually selecting the bundle inside of UN, which will tell you whether it's SUN or SUN not ZK. Yes. So you can do everything purely in 4D, just by couple a QFT to a 4D TQFT. So this is the 4D TQFT coupled to this 4D QFT. You can do everything in 4D, but another trick you can, it's more, this is more like a trick. You can uplift this thing to 5D, then write down the topological operator responsible for the charged object and the symmetry operator, and reproduce the result here, which you can do everything explicitly.
So if instead I want to do the opposite, instead of doing it directly in 4D, I want to do everything in 5D, in a sense that I want to think about unequal for superior reals and strict theory in ADS50, right? And it is 5 crosses 5.
Yes, I understand.
So then that part should somehow come, it shouldn't be added by hand, right? It should be part of some choice of making.
Yes, if you embed this thing into, yes, in the large N limit, if you have SUN, in the large N limit, you embed into ADS5, then this thing is amount to picking the diagonalization of different flux at the ADS5.
Why large N limit? I can think about.
I mean, only in large N it's ADS.
Sorry?
Of course, you don't need large N. If you don't talk about large N, then it's just the Euro SymTFT. But if you want to embed this SymTFT into ADS5 supergravity theory, you need large N limit.
Oh, right.
I mean, if it's
At any end, equal for superior reals is dual to string theory. Just the question about coupling is there, right?
okay, yes, yeah, you can do that, of course, yeah.
I don't need to necessarily think about supergravity. I want to think about
yes,
string
okay,
theory
sure,
in
yeah.
5 process 5.
Yeah, sure, yes.
And so what these choices just in string theoretical application?
Yes.
What these choices correspond to?
So this, okay, I guess I'll just jump into one example of this part, which is very nice. So in supergravity, so in 10-dimensional string theory, you have this term, B2 GC2. Sorry, I should write it here. Yeah, let me write this. Can you see this question if I write here? And then you have, let's say I have an ND3 branes. What it does it introduced this like the D3 brane, it source this an F5 flags over the S3 over the S5. Let's say I have an M5 times I start with M4 times C3, and then I can write that picture like this. This is where I put my D3. Symptotically, at infinity, I have the S5. So this is the R direction. So I can write something like, oh, this is M5 times S5. So S5 is surrounding the point like D3 in this sense. And this is introduced flux. This gives you B2, DC2, 2 pi over n. So this is how this SymTFT reproduced from the string theory topological.
But then kind of my question was more about like these different boundary conditions.
Yes, this different boundary condition is the boundary condition of B2 and C2 at infinity. If you if I only because in the QFT from string theory idea, I guess I have to skip the part. Previously, people said that if you give me a local singularity, which corresponding to some non-compact internal geometry, I can talk about some QFT to couple some gravity. But now the idea is that the local information don't really fix the QFT, don't fully capture the QFT you are talking about from string. You have to also tell me the boundary condition of all kinds of brane flux. Then I know the global form of the QFT I'm engineering here. If I only give you these 3 brane in flat space, then the best thing you can do is give me an SU and Lie algebra supermajor theory. Only I tell you what's the boundary condition of the B2, C2, which coupled to the D1 string, F1 string with volume flux is, then you know what's the global form of the QFT engineered on the D3 brane. So that boundary, and because because here you are only focusing on the topological sector of the type 2B string. In the end, after you do this dimensional reduction, it becomes a TFT. Since everything is topological, then you can make this infinitely far away boundary. You can pull this infinitely far away boundary to a finite distance. Then you end up with that picture. Then you don't care what's the physical distance between these two things because it's topological. But before you decouple every dynamical degrees of freedom in string theory, the thing you are telling me is the boundary condition of flux at infinity at R equal to infinity. And this is R equal to 0. This is where your QFT is engineered. This is boundary condition, and this is tell you the global form of the QFT. Does this make sense?
So in this ADS5 again, what is the other boundary? Because I mean, in the standard ADS, right, there is no other boundary. So
in the standard ADS5, this is just the conformal boundary. You pick the boundary condition on the conformal boundary of ADS5.
And there is no topology.
Yes, right. Yes. If you're really talking about ADS5 CFT rule, the local information, yes, right. If you're really talking about ADS CFT, let's say this is a ADS throat. In that case, you are localizing all the local information in terms of the physical boundary of the SymTFT. But in this case, you are not really talking about local information here because everything is smeared into this sort of gravity theory into here. And then you fix the boundary condition at the conformal boundary of ADS. This is how you compare this picture to that. Yeah. So there's only one boundary, and the boundary condition is fixed on the conformal boundary. Okay, I think I can move on. How many minutes do I left? Maybe 10 or 15? Okay, let me just a very quick sketch QFT from string theory before I go into some more complicated stringy example. So usually You can think of a picture like this. You have some local singularity in string theory. Okay, if you have a 10-dimensional, let's say this is some this, and this is some internal geometry. This is the symptotic boundary at infinity of your internal geometry, and then it has this isolated canonical singularity, and then the x is let's say I'm interested in a D-dimensional QFT. Okay, so x is a small space-time manifold with D-dimension, and then I have a 10 minus d or 11 minus d if you have a M-theory background x. And as I said in that picture, right, along this radial direction, you can try to rewrite this thing as the IMD plus 1 times the symptotic boundary, which is 9 minus d slash 11. And what you do in string theory is this local information will tell you, I mean, maybe sometimes it's just the singularity without any other branes. You will have some QFT here, the QFT defined on the MD. You can write the theory as something like this. So this is QFT associated with the internal geometry X. Okay, so this is called geometric engineering, or you can have something like that. You can put some branes probing the singularity. That's called the brane probing or geometric. Brane engineering, but basically is due to the X is usually we pick X to be non-compact, and then we decouple all the closed ring modes in the ball. We only talk about QFT decoupled from the gravity. So this is how usually QFT can be engineered from string theory. And then the interesting thing happens is that, okay, for these QFTs, in the field theory, usually what I do is I start with a QFT. I try to see what's the D-dimensional global symmetry look like, and then I try to capture this global symmetry by uplifting everything in one-dimensional higher into a symmetry TFT. In string theory, it's basically something like backwards, because the QFT you engineered, it's captured by the geometric information. Sometimes it is quite hard to just see from the geometric information what's the D-dimensional generalized global symmetry look like. But it's very easy to just use the geometric information to capture the SymTFT. What you do here is that you have you do the dimensional reduction along this asymptotic boundary of the geometry, and then you end up with this picture. And then you can write this, of course, you can write this in terms of the D-dimensional enclosed map. What you have is, this is now your physics boundary. This is now your topological boundary, because you pick boundary conditions here for various flux operators in string theory. And then now you have two choices. I can start saying that, oh, of course, I have SymTFT. I can just field theoretically look for all the operators which is well defined under this SymTFT. This is SymTFT. D plus 1 dimension. You can do purely theoretically, field theoretically, of course. But there is another way, or I would say a more transparent or easygoing way, is that from the starting point, I know there are many defect operators in string theory, which are branes. All kinds of branes. There are actually some in the supergravity side. There are some solitonic solutions of the supergravity, but they're just some defects in 10-dimensional or 11-dimensional string theory and M theory. And then you focus on how the topological, and then you focus on the topological sector of those branes, and you do the dimensional reduction along the branes, wrapping on different cycles, because there might be some, like, let's see, different I-dimensional, let's see, small d-dimensional cycles, which is part of this thing. And then you can have some branes whose you can have some P branes whose word volume action is defined on some MP, and then you can try to do the integral over something like that. To a D-dimensional, this is P minus D-dimensional. And then in the end, you end up with some P minus D-dimensional topological operator in the D-dimensional QFT you're interested in. Let me give you an example. So the simplest example is just that one. You know how to you know that the 10-dimensional term B2 DC2 2 pi F5 after doing the the dimensional reduction on S5 give you 2 pi B2 DC2. And where does the UM and the VN operator from B2C2 come from? I know that in string theory, I have F1 strings and D1 strings. The F1 string is electrically coupled to B2, so there is a topological sector for F1 string on its word volume, so on its word sheet, and 2. You can just have this B2 field operated right there. And for C2, you can just have similar things defined on. So this is for F1 string. This is for D1 string. And you make the F1 and the D1 string. Yes, right. Because this dimensional reduction is purely wrapping on this dimensional reduction is performed on the S5, which you don't want F1 and D1 to wrap on that. So you don't do any dimension. This is like the trivial case actually from the operator from branes. But you will know exactly like the topological action on F1 and the D1 string give you exactly the topological operator in the SymTFT in this case. There are some.
You have a not wrapping S5 just a choice? Or can you say why you because you're only interested in two-dimensional objects in the.
Yes, right. I want to talk about how the surface operator in 5D and where they come from.
So what about if the F1 were to wrap some directions in S5? What does it correspond to? Just decouple in the SymTFT?
So you don't care that you can shrink.
Yeah, right. There's no way you can wrap in the S5 because S5 it don't have any 1 cycle or 2 cycle can be wrapped there.
You're just saying it's unstable. So
you're just right. Nothing can. Even if there are some compact cycle, you can wrap in.
Yeah, what I have in mind is not entire S5, like wrapping a direction S5 and a direction space.
But what does you mean that it just?
There's no direction you can wrap in S5.
I know, but you can have it moving, right?
Yes, right.
Yeah.
And then just some unstable stuff which will in the end will be decoupled from the theory.
But it's just saying that it's non-constant S5 direction, right?
Mm-hmm. Yeah.
And I don't think you assume that it's necessarily constant, but just somehow on this 5. Just
You're saying it's parameterized. If you can project to the M5 as a two-dimensional.
right.
Yes,
Yeah.
right.
But it can move around the S5.
Yeah, in the S5 it's just a point.
Mhm.
Yeah, let me quickly give you.
And how do I see from high dimensional perspective that these are becoming topological? This is just because you're kind of
It's because you only focus on the there are dynamical degrees of freedom for this thing, but the way you do that is based on this picture. After you pick the boundary condition for B2 and C2, so either you put your F1 or D1 string something like this. It's wrapping the M2 is something like M1 times the radial direction, it will become infinitely heavy. This gives you the charged object because you have those. You can pick, if you P2 is pick a direct boundary condition here, then you can have F1 string end at infinity. This is F1, F1. This is the charged object, which gives you loss amount. And in this boundary condition, the C2, which means you can put your C2 is free, which means you can put D1 string at infinity, linking with this F1 string. In this case, before doing the dimensional reduction, everything is physical. You cannot pull this D1 string inside, saying I'm talking about its topological. It cannot be topological. You cannot pull. Only when D1 string is strictly at infinity, all the dynamical or physical degrees freedom is decoupled from the local information, from the local QFT. The dominating thing in the infrared is the topological effect of this D1. But after you do the dimensional reduction, now everything becomes topological. And now you are free to talk about the D1 string to be here or talk about D1 string to be here. And then you end up with the picture of a charge operator linking with the charged object.
So basically by key reduction.
Yes, right, yeah.
You remove all the...
Yeah, by key reduction, and then you get rid of all, get rid of everything about the 12. The only topological sector is dominant.
And also the metric diverge.
Yeah, there are
yeah,
there are no metric dependence anymore. After you do this asymptotic boundary dimensional reduction. The interesting case happens.
But you may want to say that you can do that for both F1 and D1. You can push them all to the boundary. It's not like the if you put F1 to the boundary, it becomes non-topological, but then it becomes trivial.
Yes, you can. Yeah. You can choose the, yes, right. Yeah, thanks. So you can pick all the 2 dimensions of this worksheet of F1 both at infinity. Then it becomes, the boundary condition tells you that,
fixed,
yeah, right. It's just fixed, right. So it's basically doing nothing.
I think that's
yeah. So the interesting, so another, okay, I guess this is one last example, and then I can just end. So if you have D1 branes probing a very complicated geometry, and then you reduce the 10D topological, the 10D to B string theory on this geometry times. So this is a 7-dimensional manifold. After you do this reduction, the SymTFT you get. Yeah, sorry, bear me a little. Now I'm writing everything in terms of the quotient to deal with the fact that they are all finite valued 2 pi over 2. So ABC and A hat, B hat, C hat, they are just quotient in ordinary cohomology, which you can think of every fields are strictly Z2 valued now without use of the diffusion motion. So this is the SymTFT you get from the D1 yeah, right. The asymptotic boundary is this geometry, and you put D1 branes probing this singularity. D1 brane has 2D word volume. I want to talk about 2D QFT, and then I have this 2D QFT times this thing, which is basically the 3D SymTFT box I would like to talk about, and this M3 is together with this 7-dimensional manifold giving me something like this. Okay, so this symmetry TFT is actually have many choices of boundary conditions. You can pick boundary condition A, B, C, both directly, which make A hat, B hat, C hat are both normal. This will tell you that you have a D2 to the cube global symmetry. The background field are just ABC, but with a mixed anomaly. this is what Ethan said, like in one-dimensional higher is invertible TFT tell you what's the anomaly of a two-dimensional system. You can also pick B hat, A, C hat to be derivative. In this case, you see if I compute the equation of motion for A, I have delta A hat equal to BC. For finite symmetry, I can always define a cochain. I can always define a cochain which is closed. If this is a Zn cochain, I would say this is a Zn diagonal theory for a Zn finite symmetry. But A hat itself is not closed. This tells you what? This tells you the global symmetry you're ending is G2B times G2C. Sorry, it's a group extension. This is a D4 symmetry due to the central extension. And I can try to gauge in the whole D4 symmetry, which means I flip this boundary condition into its canonical dual to be directly, and all its canonical dual fields becomes lemma. You have rep D4 symmetry. The rep D4 symmetry is non-invertible because it has a non-invertible simple object in its field category. I'm sorry being quick here. It had something like this. So this is a non-invertible defect line generating a non-invertible zero form symmetry, and this is associated to a D2 vector. This is associated to another D2 vector, and we call them B and C. Sorry, B and C. And this is just a, yeah, right. You can think of, you have a D2 times D2 symmetry. There are 4 group elements of D2 times D2 symmetry, right? It's just the 1, A, B, or A, B. And this is the non-invertible line associated. So this gives you the non-invertible symmetry because it has a non-trivial Führer rule. What's the action of this non-invertible line look like? It looks like I A hat times I hat exponential I phi cup delta phi hat plus phi B plus phi hat. I built this operator in this 3D SymTFT. I use the field in the SymTFT. And this phi and phi hat is not part of the SymTFT, but I partially them over. So this is a one-dimensional diagonal equation theory, D2 diagonal theory, but with 2 twist terms. But you partially go over phi and phi hat, so even if they're not part of your fields in SymTFT, it's fine. Because of this non-trivial path integral over the diagonal equation theory, this is a non-invertible line. You can compute its self-fusion. In the end, you will end up with this either 1 or either 2 operator, built by B field and C field, similar to the UM and B and O. This operator, of course, you can just starting with this SymTFT, you ask yourself, what's the well-defined gauge invariant operator I can build inside of this SymTFT? This is one of the answers. Or you can do it directly by looking at where all these fields come from. You realize that this A hat comes from this 3 brane on a torsional 3 cycle inside of this geometry. And then you see that, oh, of course, I want to focus on the topological sector of the D3 brane. You have C4, the D3 brane have 4-dimensional volume. So of course, it electrically coupled to a 4-form field in supergravity or in intensity theory, but it also include the lower dimensional brane charge. C2 is the flux. C2 is the field electrically coupled to D1 brane. So So this is inductor coupled. This is D3. This is coupled F1. What's this? This is the dynamical degrees of freedom come from open string fluctuation on the D3 brane. So for D3 brane, it can couple to this closed string mode, but it also has its own closed string fluctuating on that. So this is the field strength of that warm form U1 connection defined on that. And because I know it's dynamical, so in the end, I do the path integral of A1, which is the connection of this. And then you do the dimensional reduction. The M4, M1 times gamma 3. You want this thing to be wrapping on torsional gamma 3, and by some technical trick, in the end, you reproduce exactly this section. So this is, so in the end, I would like to make this correspondence, SymTFT, and the top operators. They both have their own top-down approach. This is 10D or from 10D or 11D, dimensional reduction of a string or M theory. This comes from the branes, from the supergravity side. It's some solitonic solution, but in this case, we only focus on its topological sector. I guess this is end of my talk. Thank you. Yeah, feel free to ask any questions because I know I'm like super fast in the
I
end.
never understood what is the top product. This is an action, so at the end it's a number. So can we give an example where we get a number? Let's say 2 pi times 10, 2 pi times 16.
Oh, you can.
Everything is E2 valued.
So everything is into valued. So what is A cup delta A? And what does it mean to take the equations of motion of a Z2 valued object?
There are equations for the cochains.
Yeah. I mean, I can write everything in terms of the differential form. So now everything is U1 in differential forms. And then the equation, and then you can take equation motion, right? You have A2 times dA equal to 0, 2 times d equal to 0 for A hat and everything. And then you know that because of this equation motion, you know that they're not really U1 valued, but on shell they are D2 valued. Because the operator you can build from them, I am the M cannot, the M is only in D2. If it's 2, this will trivialize this operator. And then you say, oh, how about I just use D2 valued thing to make sense of this constraints on this operator. Then you can make the trick, the U1 valued stuff. If you want from U1 to Zn, you can rewrite everything like this. Now it becomes, strictly speaking, Zn valued cochain. And then you rewrite everything in terms of the cochain language that you substitute wedge into product of cohomology, but it's just.
But at the end, if you want to write the action, I mean, like here we have a functional integral and you integrate over. So what does it mean to do this integral? Because
this integral over is basically the, yes, right. This integral is basically the sum. You sum over this from the 0th order cochain M1 to Z2. Yes. I'm writing that, yes, yes. I was being sloppy to write the path integral, but here you just sum over the 0th order Z2 valued cochain leaving on the M1. This is my operator. And then because everything is Z2, so basically in the end you will see, if you do the fusion, you will see that this is actually tell you that whether you turn on the Zn operator or not. So you only have 4 operators on the right hand side of the fusion rule.
So if you wanted, could you have written the same integral in terms of forms, but then with some delta function that tells you that the integral of A is integer value?
Exactly, yes, right. It's just if you write it in differential form, then you have to,
You have to constrain.
Yeah, right. You have to constrain the on-shell condition on this thing. Then you know what kind of operator you can build. And then you say that, oh, is there any way I can directly off-shell build this operator from some action? Then this is
It was a bit too fast for me. But is there a simple way to say, to picture to say what non-invertible symmetries are from this SymTFT, from this S5 perspective?
Yes, great, yes. So in the SymTFT, you can build some operators. So yes, great. So in the case of this, you can say that, oh, I know there are two set of operators which can be built from B to a C2. They're both invertible, right? Because they're just an integral over B to a C2. And then, but there are some complicated SymTFT, something like this. Okay. In this case, you can build some operators which is much complicated. Oh, this cannot. I'm sorry. You stare at that SymTFT, right? How can you define a gauge transformation of that SymTFT so that the whole action is well defined? Is gauge invariant? You can say that, oh, I want to define something like this. Lambda b equals to b plus delta. Or something like that. Without this mixed anomaly term, you can just define the usual gauge transformation for all the one-form field. I mean, you can just work here, all the one-form field. But with this gauge transformation, you realize that this will ruin the gauge invariant. You want to define naively. There is a way to fix this. You define a more generalized gauge transformation for A hat, B hat, C hat field, so that you cancel the gauge non-invariance introduced by this thing. I don't remember the concrete form of the A hat, B hat, C hat gauge transformation, but this actually tells you that naively you want to write an operator something like this, but because the enriched gauge transformation rule for A hat, this is not gauge invariant. If you want to build a gauge invariant operator dependent on A hat, this is the only choice you can have. Because the gauge transformation rule for A hat is coupled with B and C field.
But maybe Sergey is asking for like a more high level, like what the features of SymTFT tells you that.
Right, exactly.
Oh, I see. Okay, great, yes. Okay.
Quality, yeah.
Okay, great, yes. In the SymTFT, yes, if you have a SymTFT, you can write the spectrum of its topological operators. Some of the operators are non-invertible, some are invertible. And then you put these invertible and non-invertible operators on the gap band definition. Some non-invertible operator will be trivialized, will be reduced to invertible operator. And then in that sense, you end up with an invertible symmetry. But some gap band definition will preserve the non-invertibility of those operators. And then you know it's the non-invertible symmetry.
I think there's just no very efficient criteria, right?
But for instance, from this discussion, it sounds like generic situation to have non-invertible symmetries, and to get an invertible, you need to work harder.
That's right.
But somehow, at least so far, experience was the opposite. Like we used to have many conventional symmetries, and there are very few examples with non-invertible symmetries. So why is it? Is it better in identifying non-invertible symmetries?
I think partly yes. So many of those theories actually have non-invertible symmetries. We're just not looking at it carefully now.
Yeah.
But for instance, it's very easy, even in examples when there is non-invertible symmetry, it's very easy. Typically, they're really only conformal points or something. If you do some deformation and they're completely gone, and invertible symmetries preserved. How to see? Because here it looks like invertibility is just extra condition, so it looks like it should be harder to have invertible symmetry. So why so fragile on the deformations?
Partly because it's in this SymTFT picture, as Xingyang was explaining in this example, right? The SymTFT realized several possible symmetries, like either D4 or Z2 cube or non-invertible. And the reason that these are related in this context, they're related by doing a discrete gauging on this on the quantum field theory of interest. So try it differently. Non-universal symmetry is quite common, but it could be rather trivial. So you have a zero form symmetry, continuous symmetry. You can always gauge a non-abelian subgroup that if it's non-abelian, then you have a non-universal symmetry, but just in a very trivial way.
It just doesn't act on anything essentially.
It acts on some extended object.
Extended object, yeah, right. But if it's
I think your point is that it's very hard to have. Yeah, it's not just there's no example of a non-universal symmetry that acts in a dramatically different way on local operators in higher dimensions. I think that's
And is it from these discussions not clear why? Right?
no.
No, it's not. It's not clear from the SymTFT point of view how it is, because basically the information you need is all encoded in this physical boundary of the theory.
Yeah, it looks like indeed I agree with you. Like looks like generically you would have non-universal objects.
So either just this generic philosophy completely misses something, or we're missing some extra.
But here again, it's generic because there are some topological boundary conditions.
Yeah, right.
But the different topological boundary conditions at the level of the local quantum field theory living on this enriched boundary are related sort of by discrete gauging.
Yes.
So the point is that there is some discrete gauging that will generate non-universal symmetry. That's what this picture is telling us. But we don't usually talk about this discrete gauging because
These SymTFTs are for one form symmetry, right?
it works in general.
And the
So here, the example is about zero form symmetry.
Yeah. Here everything is a
Zero form.
differential one form, so it's background field.
Background is one.
And in 2D you gauging zero form symmetry.
I think right now, maybe related to Sergey's question before. So right now, the most usage of the SymTFT is a way to kind of organize quantum field theory with symmetries. The SymTFT realized quantum field theory as boundary condition of a higher dimensional QFT, and the relation between different QFTs with similar symmetries can be realized as choice of the topological boundary condition at the other end. So if you were to classify quantum field theories with symmetries, this SymTFT would allow you kind of peel out the symmetry part and reduce the classification problem to something that's like symmetry independent.
And also there are some dynamical consequences when you're looking at this non-universal like this generalized symmetry, because the anomaly of those symmetries will tell you in infrared whether this theory can be truly gapped.
Yeah, but that you don't need SymTFT.
Yeah, right. That's like right. You see, SymTFT is more like a trick you can do just to try to purely capture the symmetry part of the theory.
It's some way to kind of peel off the symmetry away from the QFT.
Yeah, right. Try to
So, and was there a sufficient condition for like non-invertibility for like what cycles you need to wrap or something like? Is there any geometric condition? So you just have to experiment. If you took this special like T3 brane wrapping.
Okay, it sounds like it should be conditioned for invertibility, not non-invertibility.
Yeah.
Well, generically you get something non-invertible, but then there is
generically everything. Yes, actually. Generically, if you have some non-trivial internal geometry, you have some brane wrapping the internal cycles. Generically, it will be non-invertible because the brane or volume topological the Westminster term for the deep brane has many terms, also including path integral over the open string fluctuation nodes. As long as you have the path integral part, usually it will become non-invertible. And in some trivial, in this sense, invertible symmetry looks like rare.
Yeah, which is
quite. But it's right. And then some application might trivialize your non-invertible symmetry into invertible symmetry, but still, it's I think so far it's just people are just keep producing examples. But there's some interesting thing when you talk about the anomaly of this thing in the SymTFT, because it's kind of a trick you can use to constrain the triplet gap space or not.
Is it for a drop bar?